So I think I'm actually just going to have to start with an apology for getting here late. I had a couple of lectures to deliver this morning, and jumped on a plane straight after. I'm very sorry that I missed some of the talks earlier, but it's lovely to see what people are here to talk about. So I'm going to talk about self-organisation of structure in liquid metals, low temperature liquid metals. And I'll get onto that in a second. I've got a picture here, which is a tramping photo, which is a bit of a metaphor for what I do, I suppose, on my title slide. It took me far too long to figure out that I should have been the type of scientist who got to go on field trips somewhere. As it turns out, I do all my tramping in my own time, but there's something about this idea of there being a very complex landscape that we explore as material scientists that I'm going to come back to in my talk. So one of the real privileges of my work over the last few years has been to be one of the co-directors of the McDiarmid Institute, which is a centre of research excellence looking at material science and nanotechnology, and in particular focused on addressing challenges of sustainability through understanding material sciences inherently connected to challenges of sustainability. So this is a photo of the group of us up in Rotorua at Whakarewarewa Village a few years ago, being hosted by our partners there who we work with closely. I also wanted to put this one in because Justin Hodgkiss, who couldn't be here today because he's busy with his kids on school holiday, travel is here in the middle of the photo as well, and it's been a real pleasure and privilege to work with him in this role over the last 6 years now. So what do I do? Well, this is a different version of the periodic table to the one that Claudine put up for us earlier. There's maybe a bit more imagination involved, but in some ways what really gets me as a material scientist or somebody who looks at atoms and the materials that you can make out of them is that in essence what happens when you go from one atom to the next in the periodic table, all you do is add one. It's a simple numeric change. There's an extra proton, there's an extra electron, and in many ways that's very, very, very boring. But what's fascinating to me is that qualitatively you go from one to the next and everything changes. And so in many ways the interesting problem from my point of view is trying to go from that quantitative, actually not very interesting description of atoms to the qualitative world in which we can think about every element as having its own characteristic, having its own identity, having its own natural applications and abundance on Earth even. So that's the emoji version of the periodic table. When it comes to my research, one of the things that's fascinated me for a very long time is liquid metal structures, electronically interesting materials, but that are not solid, that are dynamic and quite changeable. So these are just some beads of gallium just there to really capture your attention while I talk about this. What I mostly do is anthropomorphize atoms, right? I'm mostly interested in trying to persuade them to act in ways that I would like them to act. So I worry quite a lot about how they're feeling. And so when I talk about material science, I think one of the things I really like to get across is that we try to control material structure, but that's not that dramatic or complicated a scientific process. In many ways, you control material structure every time you put water in your ice block tray and you put it in the freezer. You change the temperature, you're changing the phase of that material from liquid to solid. And so understanding the way that atoms want to behave with respect to each other gives us the ability to control their structure through applying an external environment, if you like. So temperature, pressure. In the context of nanotechnology, you're often thinking about the number of atoms, and that can very surprisingly change properties quite dramatically as well, or the number of different types of atoms, if I have a little subscript on that. And so all of this is really just thermodynamics. and putting atoms in an environment where we can control them sort of by proxy, by persuading them to do what we want them to do. So that's kind of the goal. And so if I'm talking about liquid metals, I tend to come back to this problem as it illustrates a few key points. I was actually talking about this in one of my lectures this morning because it was a stat mech lecture and it's always quite a nice example. So gallium is this sort of very anachronistic metal, which I think is exemplified quite nicely by the idea of a teaspoon made out of gallium, which is an object that you can never use for its intended purpose. You can make a teaspoon out of gallium. You can tap it on the bench and it's hard and it makes a noise like an aluminium teaspoon or a stainless steel teaspoon would. It seems like a normal teaspoon unless you put it in a cup of tea, in which case it melts immediately, or even if you leave it in the sun on a warm day and it goes above 30 degrees, it will also melt and become liquid. But there's something quite subtle about this because that's the bulk material, that's what happens when you have many, many atoms. But when you only have a few atoms, the properties can change quite dramatically. So we have a room temperature, melting temperature for gallium, and that in itself is quite a hard thing to explain from first principles. But then we have these very small clusters of just 30-something atoms, and they melt, and this has been shown experimentally, at much, much higher temperatures. Much, much higher temperatures, hundreds of degrees higher. So up around 600 to 900 Kelvin, or 300 to 600 degrees Celsius. And so the question is why? And as somebody who does simulation using computer codes to describe these kinds of materials, the key question that always I come back to and that motivates me as a scientist is this question of why. Because we can describe what, and that's often an interesting question in some places. But for me, the question that is really uniquely addressable through computer simulation is why and how does something happen. So we know that gallium melts at this low temperature. We know and we can reproduce these high melting temperatures of small nanoparticles of gallium. And so that's what you see on the left-hand side there. There's a change in their energy as you increase the temperature, and that change means you have a peak in the heat capacity. We can reproduce the experiments, but reproducing experiments doesn't tell you why. And it turns out you need a bit of analysis to really understand this. So we have these kind of spherical objects. If you look over here, they're roughly spherical when they're solid. But when they become liquid, they actually spread out. They become sort of pancake-like structures, which is what you see. Actually, I think I can, yeah. What you see in this middle part of the plot, that they end up flattening in one dimension and stretching out in another. And so what we learnt from this example is that these two-dimensional structures mean that you have reduced entropy of the liquid state. So it's not necessarily about the energetics of interaction, but really an entropic effect where you have the atoms constrained in one dimension to this pancake. And this is what actually explains these very high melting temperatures of these very small particles. So that was where we started with low temperature liquid gallium, with a fundamental problem and an answer that was very non-trivial to figure out. It took us a while, took us longer than we thought it would, but that's science, I think. But it's turned out to become relevant in lots of different contexts. So a much more recent piece of work came out of working with some experimental collaborators in Australia, where they put very, very small amounts, so less than 1%, about 0.2% in atomic ratio of bismuth into a liquid gallium. And then when they watch it solidify, they see these patterns that form at the surface of the liquid. So the bismuth comes to the surface and creates these patterns of different types, stripes and spots and sort of ladder-like structures. And so what we've been trying to do is understand how, firstly, the bismuth is moved to the surface and then how these patterns form. It goes back to an old problem in this paper from Turing, so this idea that patterns form in nature through reaction diffusion processes. And so applying these kinds of rules to the migration of bismuth to the surface and the pattern formation is, I wouldn't say that we can predict what patterns form under what conditions yet, but we can see the ingredients, we can see the starting point for those patterns to form. And so the idea with that is, I'll go back. The idea with that is that what we're trying to do is control structure, the formation of structure in a way that's very bottom-up, that's very natural, that mimics the way that structures form in nature, rather than needing to be machined in some more complicated process. I won't talk about this too much. Catalysis isn't really the point, but because these things are dynamic, we end up having to create statistical models of how much the atoms are moving and how much that's changing their behavior. So we're very interested in these kinds of models in recent times. So I'm just coming back to this idea of complex structure, a complex energy landscape that we sort of wander around trying to find the right structure for a particular purpose, or the right place in which our atoms are going to self-assemble in a way that we want them to. And so there's this quite old piece of work now that I did many years ago. This was actually when I was working out at IRL that this paper was published, with this hexagonal form of zinc, which it turns out is, there are sort of two different hexagonal forms. So these lakes were metaphors for these basins in which these materials form. And much more recently, again, these Australian collaborators of mine who work with liquid gallium found that they were able to create snowflakes of zinc, but within liquid gallium. So where the zinc would come together and grow into a crystal structure that you wouldn't find under any other conditions. And so I'll use this as an example, mostly just because the snowflakes are very pretty. There's another one. Oh, I think there's even another one. These ones have 12 branches instead of 6. They're all very pretty. And so what we did was to run some simulations. I thought just put in one little movie so you can see some atoms wiggling about. And so you have a liquid environment. This is the grey atoms. They're all liquid and dynamic. And the blue atoms are zinc. And they maintain a solid structure in the liquid. But there's an interface there. And what that interface does is it means that there's I'll jump past that because that's just about the disordering, but I think you see it better on the snowflake itself. So here, the six-fold symmetry is an interface of the solid with the liquid gallium that is stabilized, as we see in our simulations. You can sort of see that's this one down here. And along this branch where the snowflake arms are growing, you actually have a structure that's significantly destabilized by the contact with the liquid. And so it's sort of continually being eaten away in between those snowflake branches as the crystal is growing. So we're able to show really from first principles, using the interactions between these atoms, how different types of structures form. A really key example was that even though zinc is hexagonal, not everything that is hexagonal will make snowflakes. So this is the example of crystals that are produced from a silver gallium intermetallic material, and they actually create rods even though it's also hexagonal. And we could explain that quantitatively by looking at the energies here, which you don't need to know anything too much about in detail, other than that the facet that's eaten away in the case of zinc is the one that's stabilized in the case of silver, and vice versa, and so the crystal grows in a completely different direction. So I think I will leave it there with just some acknowledgements to the many, many people who I've worked with on these types of problems over many years. To my experimental collaborators in particular, thank you. The Marsden Fund, who supported that very first piece of work on gallium clusters that got me going in this direction, and to everybody in the McDermott Institute that I've had the pleasure of working with over many, many years. Thank you.